So in our last video, we started talking about subatomic particles, and we said there was 3 different types of subatomic particles that our atoms are composed of. So we had protons. Protons have a positive 1 electric charge. They're found in the nucleus. We had neutrons. Neutrons are neutral. They have no electric charge. They're also found in the nucleus. And the mass of a proton and a mass of the electron are very similar, so very similar masses. We also had electrons. We said electrons were found outside of the nucleus. They have a negative 1 charge, and they're very, very light compared to that of a proton or a neutron. I had put down about 2,000 times lighter. I think it's closer to 1,800, somewhere in there, but essentially very light compared to protons and neutrons. We also talked about our atomic number. Remember, our atomic number tells us the number of protons in the atom's nucleus. And then also remember that the number of protons defines an atom as belonging to a particular element. So if we were to change the number of protons, we're actually changing what type of atom it is. So lithium always has 3 protons in its nucleus. If it didn't have 3 protons, it wouldn't be lithium, right? If I was to add a proton, I would have beryllium. If I was to remove a proton, I would have helium. So the number of protons is what tells us what type of atom it is. And we said these were the whole numbers on the periodic table. So if we want to know how many protons a particular element's atoms have, we just find its atomic number on the periodic table, and that tells us that information. We also talked about the mass number. The mass number is also a whole number, right? Our mass number tells us the number of protons plus the number of neutrons in the nucleus. These we said were not on the periodic table, right? They're counting numbers. We can't have fractions of particles, right? I can't have 0.234 protons or 0.76 neutrons or a half or any sort of number other than whole numbers. So these are also always going to be whole numbers, right? They're counting numbers. I had said we would talk about that other number on the periodic table, and that's what we're going to focus on in this video. And that other number is our atomic number. Sorry, atomic mass. It's easy to get these all mixed up. There's atomic numbers, mass numbers, and then atomic masses. So atomic mass, be careful. Don't goof up like I just did. So we want to keep these straight, right? Atomic number, number of protons. Mass number, and this one is where people get confused between mass number and atomic mass. Mass number is a number again. So I would focus on this number part of it to keep it straight, right? It's the number of protons plus the number of neutrons. Atomic mass is actually what is the mass, right? If you were to weigh it, what does it weigh? What makes it a little bit more complicated than just that, however, is that not all atoms of the same element have the same mass, right? We talked about isotopes also in the last video, and isotopes were atoms of the same element that have different masses, right? Their mass numbers are different. They have a different number of neutrons. So carbon with 13 particles in the nucleus versus carbon with 12 particles in the nucleus are going to have different masses. So if we want to know what is the mass of that atom, it's going to be an average. And it's not just a straight average, it's a weighted average. So most carbon that exists in nature is carbon-12. There is a little bit of carbon-13 and then trace amounts of carbon-14. So if we were to do a weighted average mass for carbon, it's going to be a lot closer to 12 than it is to anything else. And if you look at the atomic mass on the periodic table, for carbon, it's going to be listed as 12.011. So very close to 12 because carbon-12 is the most abundant isotope, a little bit bigger because carbon-13 and 14 do exist. So this is a weighted average. So the weighted average mass for all of an element, naturally occurring isotopes. So if we were to look at an element and we say, okay, what are its different isotopes? And then we were to take into account their percent abundance, do a weighted average, that's our atomic mass. This is the other number that's on the periodic table. And then our units, this is the lamest unit in chemistry. I say lame because it's so not creative. So the unit for atomic mass is literally atomic mass units. So instead of measuring it in kilograms, right, that's our SI unit for mass, or pounds or something else, our unit name is literally atomic mass unit, abbreviated AMU. So atomic mass units. So I want to go through a calculation. How do we calculate atomic mass? So I'm going to give us some information here. So we're going to have our isotope. We're going to have the isotopic mass. So what is the mass of just that isotope? Not our weighted average, but just that isotope. And our units on this is going to be atomic mass units also. And then we're going to have our percent abundance. So in nature, what percent of, and I'm going to do it with neon, so what percent of neon is in this form? So 3 naturally occurring isotopes for neon, neon 20, neon 21, and then neon 22. And neon 20 has a mass of 19.9924 atomic mass units. 21 is 20.9938 atomic mass units. And neon 22 is 21.9914. My percent abundance, most neon in nature is in the form of neon 20, so 90.48%. Only 0.27% for neon 21 and 9.25% for neon 22. So when we do calculate our atomic mass, it's going to be closer to 20 than it's going to be to 21 or 22 because most neon is in that form. So our formula for calculating it, so our atomic mass is going to be the sum, so our sum sign, of the fraction of abundance multiplied by the isotopic mass. That's a parenthesis, sorry. So essentially what we're going to do is, and I know this isn't a word, but it works for me, is I'm going to unpercent it, right? We want the fraction of abundance, not the percent. So instead of taking 90.48, I'm going to take 0.9048. So I'm going to unpercent it, right? I'm going to move my decimal place to the left 2 places. I'm going to take that, I'm going to multiply it by its corresponding mass. So 0.9048 multiplied by 19.9927. And then I'm going to do that for all of them. I'm going to unpercent it, so 0.0027 multiplied by its mass, 0.0925 multiplied by its corresponding mass, and then I'm going to add all of that together. So let's set that up. Ooh, not with my highlighter. So 0.9048 multiplied by 19.9924 plus, actually let's do it vertically instead of horizontally because we'll have more room that way. I'm just going to erase this and rewrite it. So I need to be able to see it. So 0.9048, again unpercented, multiplied by 19.9924, 0.0027 multiplied by 20.9938, and then 0.0925. Again, we're just moving our decimal place to the left 2 places, dividing it by 100, whatever works for you. 21.99414, sorry. And then all of that gets added together. So be careful with significant digits. We're doing both of our rules here. We're doing our addition and subtraction rule. We're also doing our multiplication and division rule. So I'm actually going to work through this one the first time with you in just the steps. Normally I would just kind of do it all in one step and then I would round to the right number of sig figs at the end, but I want you to see where the different rules are coming from. So I just grabbed my calculator. I'm going to do this with you. So I'm typing it into my calculator right now. So 19.9924 multiplied by 0.9048. And when I do that, I'm getting 18.09. So I want 4 significant digits. I have 4 here, and then here I have 1, 2, 3, 4, 5, 6. So I want 4 in my answer for this step. So I get 18.08912352 in my calculator. When I round that, that's what I'm getting. 0.0027 multiplied by its number. Now, if you don't want to round after each step, I'm totally cool with that. In fact, I normally don't. I'll keep it all in my calculator and I'll round at the end, but you do need to be able to keep track of your significant digits as you go through. So sometimes it's easier if you actually do intermediate steps like I am. So when I get this, I have 0.057, and that's correct. This one I only want 2 significant digits. I have 2 here and then way more than 2 there, so 2 in my answer. Remember, those leading zeros, the ones that come before non-zero digits, are not significant. And then 0.0925 multiplied by 21.9914. And then this one, I want 3 significant digits. This is 3, this is more than 3, so 2.03 would give me my 3 significant digits. Now, when I add these together, our rule is the number of digits after the decimal place, or after the decimal point. So here I have 2 digits. Here I have 3. That 0 is not significant, but it's still a digit. And then here I have 2. So when I add them together, I want 2 digits after my decimal point. So 18.09 plus 0.057 plus 2.03. I get 20.1, I'm just going to write everything down at first, 177, but then again, for sig figs, I need to round it to 2 digits after the decimal point. I need to include my units, and I get 20.18 as my answer. So again, be careful with significant digits. If you want to round this all at the end, that's fine. You may have come out a little bit differently than me. It should be really close though. Usually it's within like 100th place. But the sig figs should be this. The only thing that could be different is you could have 20.19, like that sort of thing. So just be careful. It's really tempting to just look at these numbers that you're given and say, this is 2 sig figs, that's my smallest, and then just give me 20. I guess you'd have to put it in scientific notation to be able to get the right number of sig figs. So 2 sig figs is my answer. It needs to be 4 in my answer. And that's because of this addition rule that we're doing at the end, right? 2 after the decimal place, 3 after the decimal place, 2 after the decimal place. So 2 after my decimal place is what I want for the answer. So kind of the two biggest mistakes that students make on these, one is significant digits. The second one is forgetting to unpercent this. Again, I know unpercent isn't a word, but it works. So instead of multiplying it by 0.9048, they multiply it by 90.48. And then your answer is way off. You can look at your periodic table to find out what the answer should be. So if it comes out to be like 2000 and something, and you find your periodic table and you look at the atomic mass of neon and it says 20.18, you goofed up somewhere, right? Go back. Your answer should make sense. If your answer doesn't make sense, please go back and check your work.